through 12 in chapter 14. So this was one of, when you took the first exam, this was one of the options for the pathways that you drew, right? So we went from L-methionine, and then we went from S-adenosyl L-methionine, and then we went to S-adenosyl L-homocysteine, and then we went to L-homocysteine. So what I wanted you to see through that whole pathway, and we skipped the enzymes at the time, but what I want you to see before was, here was our methyl group, right? The end result of this whole pathway is no more methyl group. We took the methyl group off of methionine and we were left with homocysteine, okay? So, look at what's over here helping in these reactions. Methionine synthase, N5-methyl tetrahydrofolate gets converted to tetrahydrofolate. Okay, we're going to talk about betaine when we talk about choline. But, so what's happening, right? Like if you're going, so where is this methyl thing going? It goes over there, and then it gets converted back, and then this one carbon can move to do something else. So I'm going to flip the page. We didn't do as much about this diagram before because we looked at the specific molecular structure because I wanted to focus on that methyl group. But when you go all the way through here, so you make all the way down here to homocysteine, and then you can go all the way, you can keep going and keep going and keep going, and then you can actually end up all the way down here with propionyl-CoA from L-methionine. So there are all, and they didn't put the THFs in here, but there are all these different things that you can do if you can get from methionine to homocysteine. Okay? So, but you have to be able to go in both directions. You have to be able to take homocysteine and put the methyl group back on. How do you put the methyl group back on? Methionine synthase. You've got this 5-methyl tetrahydrofolate. It's sitting there with the CH3 group. You take homocysteine and you run this backwards and you add the CH3 back on, you get methionine. Why do you want to do that? So there's something called hyperhomocystenemia. Hyperhomocystenemia means that you have too much homocysteine, you can't run the reaction backwards, and you develop, it can cause health problems. Also, if you can't go backwards, so methionine is it's essential, right? Like you need to take methionine in. If you can't go backwards, you have to take more and more methionine in because you can't recycle. And methionine, this is not the only thing that methionine is used for. Methionine is not just used to donate its methyl group. We need it as an amino acid in multiple other places. So if you can't recycle, your methionine needs go up. Okay, so take home of all of this little picture. Notice the methyl on the THF. That's what we're focusing on right now. We're moving it around. Okay, let's go back to THF. So before I turn back to my outline, so this, don't worry, you're not memorizing this.
Jesus.
Right. This is how important our ability to have folate is. These are all the different forms that we use, and these are all the different pathways where we have to get it. Okay, so this one we just looked at, and let me see if I can get it as big as possible without sacrificing any kind of function. This little one right here, methionine to atomid to HCY to homocysteine, right? The adenosyl S, all those things, that's what those stand for. So what are we doing? Why do we need methylation reactions? So that's where we can go methylate our DNA. We can get those methyl groups, we can go methylate DNA. We can methylate a ton of other stuff too, right? We can methylate an enzyme and change the way that it works. We can methylate all kinds of things. CH3, that methyl group, happens to be very effective at changing the way something folds or something attaches. It's a good shutter downer. What is CH3? Right? It's pretty nonpolar. Right? So if you just attached a CH3 to an area or a domain of a protein, or say your nucleic acid chain in your DNA, you're going to impair the ability of some other protein or some other substance to attach to it. It's going to detach, pop off, not be able to attach in the first place. Because you've just taken something that probably depends on some sort of chemical attraction and nonpolar. You've changed it from polar to nonpolar. You've changed it from something that attracts something that has an ability to move electrons around to something that attracts something that doesn't. So that's why methylation is so useful in many different areas. Let me zoom back out so we can look at this big thing again. Like I said, we are not memorizing all of these specific things. We're going to talk about this DUMP to DTMP thing, but not the pathway, just the end result. We've already talked about this in 417A, so I want to freshen your mind that you take methionine, you pop off that methyl group, and you create homocysteine, but you can run that reaction in both directions. You can make methionine back by putting a methyl group that is attached to tetrahydrofolate back on. So we have this system so we can keep moving those methyl groups and put them where we need them. Okay, so, and then you can go all the way down here, and then we're in the mitochondria, right? And then we're looking at all this other energy stuff. And we'll attach this more when we do choline. We're just going to focus today a little bit on that and not that. But it's all over the place. Okay, so in the methionine cycle, right? This is what I was showing you before. 2 steps. 5,10-methylene THF to 5-methyl-THF. This is where the MTHFR enzyme works. Methylene tetrahydrofolate reductase enzyme. So you have a 5,10 methylene THF, which means that on the 10 group you've got a methylene. So if we go back and look at the picture. Okay? It means that 5,10 methylene. What's methylene? CH2, right? So in here, right, you've got a CH2 attaching these two things. So what do? You reduce it. Because it was attached, and then you go to 5-methyl-THF. When you have a methylene group, it's bound in the middle. It's not a methyl group, and you can't just pop it off and move it, right? You have to make it a methyl group to pop it off and move it. So to do that, we use this enzyme. Methylene tetrahydrofolate reductase enzyme, MTHFR. It takes that bond that's associated between the N5 and the N10, that CH2, and it makes it so now you have N5CH3. That means that carbon group is ready to pop off, that methyl group. The methyl group is added to homocysteine, resulting in methionine. We talked about that as well. This is going in the other direction. When you've got homocysteine, you take that methyl group and then you add it to methionine, and then methionine can travel and go give it up somewhere else. And that's using methionine synthase. Now we're going to talk about B12 next time. Okay, so, but this is the only reaction capable of moving the methyl group on 5-methyl-THF in mammals. So we've already talked a little bit about how important that methyl group is. We have to be able to move it. If we can't move it, we can't go methylate our DNA, right? We can't go methylate an enzyme. We have to be able to pop that CH3 off, and this is the only way we can do it. Okay, what is this? It's important for freeing homocysteine to be available as a methyl carrier for other reactions. And some tissues export homocysteine for conversion in other tissues. Why is that important? Because if some tissues have extra CH3 that's not being used, and some are using just a ton of CH3 to methylate stuff, it means that instead of building up homocysteine, which can be toxic, you can send it out, and then another tissue that has methyl groups to spare can convert it to methionine. So, the end result of this whole thing. All right, so let me sum this up.